Alex is a Rust compiler engineer who somehow ended up working on a financial database written in Zik. When I asked him about that journey, he told me that what attracted him to Tiger Beetle wasn't even the language. It was the culture and principles. He said the language doesn't really matter much. What really matters is the culture, principles, the context in which you apply a language. In this conversation, we talked about building infrastructure that lasts, why he does weekly releases every Monday, and this beautiful idea that if you optimize for quality, you actually optimize for speed of development too. Because over time, all those shortcuts you took before will slow you down. He also broke down static allocation in a way I had never heard before, comparing it to making sure water stays constant in a bathtub. You don't count every molecule, you just make sure the tap is closed and the drain isn't leaking. And when I asked about his energy after an hour of non-stop insights, he said, I just love programming. You type something, pixels light up, and it's useful. This is the most incredible thing. Alright, this is the TigerStyle Volume 2 with Alex, aka matklad from Tiger Beetle. Let's get to it. Welcome, Alex. I'm really excited to have you today, and thanks for joining the show. This is like the last recording we are going to do for this year on the show, and I'm really excited that it's with you. So thanks for joining. Let's start with a little bit of introduction. I'm curious to know about your background, about how you ended up working at Tiger Beetle, and all of that.
Yeah, thanks for having me, Katie. And it's really is exciting to share more of TigerStyle, Tiger Beetle with people because really the high level answer to the question of how I ended up doing what I'm doing right now is that Tiger Beetle is really interesting. It's basically a captain for C++ programmers. Yeah, but for the intro, this is fun because I'm actually a Rust compiler engineer. So my entire career was writing Rust, writing IDEs for Rust, type checking, name resolution, that kind of thing. And I honestly kind of don't know how I ended up being a database developer and using Zik full-time. But actually, the answer to that question was TigerStyle, because someone told me about Tiger Beetle. I went to the repository, I read the TigerStyle, and I realized, hey, actually, this is kind of the way I want to write my programs after being in the industry for about a decade, after learning some stuff what I had half-baked ideas about how to make programming more enjoyable, more reliable, more of a engineering and craft rather than this breakneck throwing code on the wall was actually pretty close to those ideas in TigerStyle. So I realized that, hey, this is a match between me and the project, and this is how I ended up working on a database. And switching the language from Zik to Rust was kind of an implementation detail because the language doesn't matter much. What really matters is the culture, principles, the context in which you apply a certain language.
Hey there, quick note before we continue. If you are finding this kind of content valuable and want to support the Geek Narrator, consider joining the channel membership. Members get access to some extra series I've been working on, like database internals, JVM internals, and soon Postgres internals. It really keeps the channel going, and I would love to have you there. All right, now back to the episode. Perfect. And sounds like you got a great fit. And since you mentioned language doesn't really matter, would you choose Java for modern systems programming though?
It really depends on the context, and it really depends on the definition of systems, because people use systems programming in at least two different contexts. One context is low-level programming, where you really have tight resource constraints. You build some relatively simple system, but a system which needs to be perfect. So kernels, drivers, low-level utilities, which are included then in higher-level languages like Java. And for that sort of thing, Java is not a good fit, not because of the language, but because of the runtime. Because Java kind of presupposes garbage collection, it kind of presupposes just-in-time compilation. And while you could imagine an implementation of Java which is ahead of time compiled, I think actually GCC at one point implemented AOT for Java, it wouldn't really be a good fit to the language. And you need those low-level, ahead of time, sans garbage collection facilities to really go to low-level aspect of systems programming. But that's not the only way people use the term systems programming, because often people use it literally. Systems programming is programming complicated systems, especially systems which are distributed, where you have like many components and they communicate with each other to solve a particular issue. Essentially, you could say that systems programming is writing any program which communicates with other programs rather than with users. So for example, compilers. Compilers are actually very high-level programs. They don't need access to hardware. They are essentially like glorified human manipulation. That's what a compiler is. You have like a stream of input and you have a stream of output. And actually there, Java is pretty fine choice. I mean, my first Rust compiler for .NET was written in Kotlin, which is like a reskin of Java. And that was like a good fit for language. And if you think that is systems programming, then yes, Java also works there. I guess really like, I might not really like the question because, you know, this is a question about labeling. There is like a certain pile of facts about the language, and then there is like a certain pile of facts about a problem, and you kind of like attach a Java label to one pile, systems programming label to one pile, and you ask, hey, is Java good for systems programming? But actually, it makes sense to go deeper and to understand like which aspects of Java, like garbage collection, heavy one-time dynamic dispatch, which creates the standard library, affects like which aspects of your program. Because
Yeah, I think I understand, and I'm aligned with that approach. I also don't like labeling particular language because each language has its strength and weaknesses. Okay, coming back to another point that you mentioned, that you always wanted, so you sort of had this mental model of how you want to program, and then it sort of aligned with how TigerStyle was defined, right? What made you create that mental model before even reading about TigerStyle? And I think with that, I wanted to ask, what kind of problems did you face that, realize, okay, this is the right way to think about solving a problem?
Yeah, this actually goes a little bit back to what Joran was talking about on the previous episode, TigerStyle Volume 1. And that was like this idea that programming is magical. Programming is magical because you write your program once, and then you run it thousands of times, millions of times, on millions of devices. So that means that you have a very large multiplier to your effort. You could apply a little bit more thinking, a little bit more design. You could arrive at a slightly solid program. And when you do this, you actually have to fight exponents because, a linear increase in quality requires an exponential increase in the effort. But because what you're working on is not a single physical artifact which cannot be copied, but rather a program which can be copied virtually for free, that means that this exponential effort for linear quality gets multiplied by the exponential impact. And that kind of evens out. And that the fact that this is what is most exciting about programming made me want to work on systems which have this property that it's not a throwaway code which you quickly write, throw out there to experiment with, and then you pivot to something else, you do a new feature, you kill the old feature, you iterate fast. No, I realized that I personally just enjoy more building complex systems over time. Because I had that experience with IntelliJ Rust, I had that experience with Rust Analyzer, where you start with an empty file, there is nothing. And then you spend half a year on that, and you get a parser, and a parser does nothing, it's not useful. But it is, at least more than an empty screen. And then you think okay, so let's add an LSP server to that parser, and you add a no operation LSP server, which also does nothing. But then maybe you get some primitive completion, some primitive expand selection, and by adding this grains of sand over time, you realize that, hey, you actually arrived at a pretty complex piece of software which solves real world problems. And my personal experience is that I kind of like was in that like startup mentality is that like iterating very fast is important, experimenting is important. So a lot of my previous code was written in this style of like trying to deliver more features as quickly as possible and not like, necessarily like cutting corners, but also not explicitly thinking through how the code will be used in 10 years. And well, to be fair, in the context of Rust Analyzer, that was like an explicit idea to not think about how the code will be used in the future, because the whole idea at that point that Rust Analyzer is going to be an experiment to show how you could write an IDE with the goal of providing data about how we should be modifying the upstream Rust C compiler. So the idea was like, there's like a couple of years of Rust Analyzer, everyone understands that, hey, this is how an IDE should be working. And then like, a couple of years later, Rust C becomes pretty much re-railed on the architecture using Rust Analyzer. That kind of like didn't pan out, and that piece of software is still used by many people all over the world. So they are now paying tax for mistakes I was making. So that's kind of like was a journey which made me think like, gee, it would be like really cool to work on something where you know that, hey, actually, this is really a long-term project. There is no cutting corners. You actually do apply this exponential effort to get even more exponential result because you are building this infrastructure. So yeah, that's what I realized is that, hey, I want to build infrastructure. I want to build code which is used for many years. And if you think about like, okay, so what is important for infrastructure, you realize that, hey, what is important for infrastructure is quality. And if you think about, hey, how do I get quality? How do I think not in terms of time deadline, but in terms of quantity deadline, you more or less arrive at the principles which are outlined in TigerStyle. Because TigerStyle can be summed up really succinctly, and that is like, do a good job. That's really it. Don't just like, solve a problem. Don't just ship a feature, but really do it in the best way you can think of and try very hard to really thoroughly think about everything.
That makes a lot of sense. And I'm going to ask you probably a similar question, what I also asked Yoran, but, probably go slightly deeper, right? So when you say that, okay, I want to solve or optimize for quality instead of like time deadline, I want to have like something solved in the best way possible. But how do you not get into a situation where you never ship, right? How do you know that this is the perfect quality? I cannot do better. Like when do you say that, okay, this is good enough?
Okay, I guess there's like one practical tip here and a bunch of philosophy. The practical tip, and I cannot stress this enough, it is like my silver bullet, my secret superpower, which I arrived partially studying what Rust was doing and partially just applying my thinking, which like really multiplied my work since then. And that is, you do a release every week. That's it. Every Monday, you just go and release whatever code you have in the main branch. And this is really an incredible multiplier for actually shipping, because everything gets shipped within 7 days. So there's like no question of just like iterating. It's of course there is this opposing force here in that if you know that your commit today is going to be shipped in less than 7 days, then you need to make sure that your commit doesn't break production. And that forces you to work and think in terms of incremental improvement, in terms of making a simple system that works and then slowly expanding it to a larger system that works. So there's no contradiction here, because you don't have to build everything from the start. If you try to build a fully fledged version of the system, you will get stuck in analysis. No, you need to start with a minimal valuable product. You need to start with something which is correct, even if it doesn't fully solve your problem. and then you can incrementally work on it. So like, as a simple example, just on day one, you write public static void main if you're using Java or like whatever is, although I think today like you actually can write that shorter. It's just like, there's like, when I was like learning programming, of course, Java was my first language. And when I was learning Java, I didn't really view programming at all. So like public static void main was really like a spell from like a Harry Potter or something. I didn't like really know like the meaning of words, especially given that like, English isn't my native language. So at that point, like, there's like also a language barrier. So anyway, this kind of like etched in my brain. Like when I think about main, I think about public static void main string args. Anyway, and so like you like write just an empty main function, which returns with 0. And you ship that. And I mean, this is like solid, correct program. It doesn't have bugs, like you could release it. It is that. It, of course, doesn't have all the features you needed to have, but then that's all the other follow-up weeks where you go and you add features to your thing. Okay, the question, that's kind of like the practical advice. Just quickly release this really like simple trick. The more like high-level philosophical thing is that I think it's really worth thinking about the context, and it's really worth thinking about the problem. Because again, what we do with TigerStyle at TigerStyle is what we believe to be the best way to build a distributed data system for financial transactions. And if you are building a distributed system for financial transactions, apply TigerStyle as is. If you build something else, then by all means, go read TigerStyle, steal ideas from it. But do not necessarily try to apply those ideas literally, because in some cases, it is way more important to iterate, to try things out, than to do like a really solid job. Because actually, we are having it like extremely easy at TigerStyle. We are implementing double entry financial accounting. And people have been iterating on this schema for accounting for like, I don't know, half a millennium. I mean, it's really like the reason why we invented writing was actually to record transactions, to do accounting. So the problem domain is extremely well understood. And we can cut that part from what we do mostly and focus on the technical artifacts. In some other domain where you don't have the privilege of working with a domain modeling problem which is solved for you by generations of people behind you, you might want to apply different tools. But yeah, still, my advice would be to try to go from a simple system that works to a complex system that works. Try to slice your features into manageable chunks and make sure to cut on all the accidental complexity. Because actually, I mean, programming is not hard. It is hard, but like, it's just like writing text. What is hard is that there is often a lot of accidental complexity to actually get the programming done. Like if you just sit there and write code, you could write a pretty decent amount of algorithms or whatever in a relatively short time. What actually prevents you from doing this every day is like, okay, so now I need to build my code and my build takes 10 minutes. Okay, I need to wait 10 minutes. Now I need to submit my code to the CI, and CI is like another 4 hours. And then I need to request a code review, and the culture in our company is that our code review takes a week. That's why it becomes hard to ship code. That's why you got stuck without shipping, not because like you are over designing things or you are going well beyond the quality you need to achieve, but because you have some issues in your process. There are things which just prevent useful work from happening, which is, again, weekly releases are like a great multiplier there, because one like huge time sink for many teams is like the process of releases. Because once in a while, a release happens. And when the release happens, everyone needs to go through a release process. They need to figure out what goes into the release, what doesn't go into release. They need to like release nodes. They need to coordinate with release manager. A release manager like is an entire person who is distracted from their usual responsibility. That's like a lot of work. Don't do this. Just make automated releases every week. And conversely, make sure that your testing infrastructure is solid enough that you are comfortable doing that. So yeah, that's kind of like how I would think about this problem in general.
Yeah, I think that's really powerful. And so you don't start with a deadline, you start with a feature and then have a deadline on top. Let's say your release cycle. So you still ship, but you still focus on a very small part for, let's say, an entire week. And while you were explaining that, like public static void main and, start with the simplest possible, thing that you can write and make it work and then process it incrementally. Some of the ideas align really well with, let's say, test-driven development, right? Do you use it? What are your thoughts on that? Because it aligns with incremental thinking. It aligns with designing whatever you're trying to do before you can actually code, and also writing tests in the process and making it green and, following this cycle of red, green, refactor. So what are your thoughts on that?
Yeah, okay, this is a very funny question because I was confess that I'm at the limit of my English grammar here because I have written a blog post which I will hopefully publish the day after tomorrow. But by the time, so that's in the future, but by the time the viewers will be watching or listening to this episode, well, it will be in the past. But anyway, yeah, I'm actually touching in that topic there. The idea here is that, okay, so some people talk about like test-driven development. And then when people say, okay, like test-driven development is not like good idea, like you want to do test-driven design. The purpose of this red-green refactor loop isn't so much to shift working code, but it is to hint what should be the shape of your code. Because if you make the code testable, it actually usually correlates really well with good design. And I had a problem with that. I had a problem with that because I do think a lot about testing, and really like what really attracted me to TigerStyle was this idea of deterministic simulation testing. Not because it is some like brilliantly new magical technique. No, it's like, very obvious thing. And I always wanted to do this. The problem was I never found like a place where like, not only I was like, hey, let's do deterministic simulation testing, but everyone on the team was like, hey, let's do deterministic simulation testing. Really, like when I was chatting with TigerStyle for the first time, what we ended up doing is showing each other our deterministic simulators, because I also was like working on like tiny distributed system in my spare time just to understand how to build those systems. And I had this like deterministic simulator, they have this deterministic simulator, I was like comparing our nodes. Mine was actually better because it did minimization, and Whopper to this day doesn't do minimization. So anyway, okay, I'm
Test-driven development.
Yeah, okay, so, yeah, sorry. The problem is, when I design software, and it was true for Rust Analyzer, and it's true for TigerStyle, and it is true for that distributed system I was playing around, and generally, it is true about every piece of software I'm writing, is that I do 99% of test-driven design before I write the first line of code. Because the way I approach problem solving is that I think, okay, so I want some problem solved. I want completion in my Emacs for Rust. So how do I solve it? Then I think about what actually needs to happen. I need to read a bunch of text files, and then I need to do some parsing, type inference, whatnot. Then I need to spit out some JSON, which tells me what are the completion parameters. And then I also need to not be slow to redo all this work. Then user types one single character and asks me for completion again. So there's needs to be some kind of incrementality to this work. And after I realized what is the input data, the text of source files and the stream of edits, and what is the output data, like that JSON behind the completion widget, the second thing I do, I think about how I can test. Because if I write my LSP server, and the way I test it is that I run it in a directory full of source code, and then I interact with it through my editor, it's going to be super slow. Because I need these processes, I need tons of input output. I will have to depend on my TigerStyle library. This is not how I'm going to write a test suite which will be fast and which will allow me to write tens of thousands of tests, which allow me to ship every week, because that's what I want to do. And so instead I think, okay, so I'm not going to use my real system. What I want to do for my tests, like in this case, is actually, in my test file, specify a tree of source files in line, and then I want to run my completion, and then I want to diff the result in JSON against, golden file. So I don't want to spawn any process at all. I don't want the editor. I don't want cross-process communication. I want to just check a single function with the signature string arrow string. That's it. And once I make that realization, I then design my system such that it is a pure function from string to string. And then, 4 years later and 10,000 of tests later, every test still looks like string to string. So this is, I think, like test-driven design. You realize that, hey, you want to test your system, and you realize that, hey, if you test your system, but you also touch 10 different external systems, then your test will be slow, be brittle, and brittle in the sense of failing, in the sense of flags. Sometimes the API you're calling is having a bad day, and your test fail for no faults in your code. And C, brittle, in the sense that the external code is going to change. And you'll have to deal with those breaking changes. So you'll have to constantly adapt your tests to changes in your development. So you want to avoid that, and that's why you architecture your software such that all the dependencies are, first of all, explicit, and B, can be entirely in memory. Dependencies which minimize access to anything outside of your system. And that is, in the nutshell, the idea behind deterministic simulation testing. It's all about designing the interfaces. It's all about removing dependencies. And this thinking really is driven by this idea that I want to have test suite which is super fast and super reliable. So one of the things I'm really proud of is that, well, I'm not sure how it is right now because I haven't touched Rust Analyzer for several years at this point. But when I still was actively participating in that project, I think our test suite contained about 10K tests, and it was running in 7 seconds, the entire test suite. This is really was an indication of the ideas I had when I started working on that project. Because my first system, the IntelliJ Rust plugin for JetBrains IDE, it actually did suffer from that problem that I didn't properly isolate the interfaces. So a lot of tests depended on a bunch of IntelliJ internal stuff. A lot of tests depended on running cargo as a subcommand, depended on having the sources from the Rust standard library as a part of the test. I'm like, okay, which version of standard library, which, changes it to releases. And that made those tests pretty slow. Well, okay, maybe part of that also was Java and garbage collection and warm up, because I think JVM is pretty bad for tests because every test executes new code path and you essentially do this Git warm up, whatever. But anyway, my point being is that tests in IntelliJ Rust were okay, but I didn't really love them. And for Rust Analyzer, I decided, okay, so I kind of want to be really strict about dependencies. And then TigerStyle is kind of the next evolution of that, is that you still take this idea of avoiding dependencies, but then you also add this idea of pervasively using randomized generated inputs, rather than writing a bunch of unit tests by hand. And Rust Analyzer is a bunch of unit tests written by hand, a whole bunch. But by hand, you go to this idea that, okay, let's ask my computer to generate tests for me. And this kind of really supercharges this idea, because now you could have not tens of thousands of tests, but probably billions of tests at this point. I don't know how many runs of TigerStyle's simulator we had in total, but I would guess that it actually is in the billions because some time ago I did debug a failure for us, which boiled down to our random number generator returning a number, 32-bit number, with all bits set to 1. And yeah, we had a bug in our tests which failed if random number suddenly is a complement to 0. And I was staring at that and with disbelief, thinking, hey, maybe it's actually like my random numbers generator was buggy, but after some investigation, I concluded that, yeah, I really was like 1 in 4 billions like there. So yeah, these are my thoughts about test-driven development. Yes, like by the name, it is extremely powerful intuition pump to actually design good interfaces. But I don't really follow this red-green refactor style of the loop. Of course, I like do that, but that's not interesting. That isn't what defines my system. What really defines my system is that initial thinking about how everything fits together and how the big invariants hold. So just to give you just one example of those properties you could decide to have or decide not to have when you build big systems. Coming back to Rust Analyzer, like this use case for a compiler which works on the code which is constantly modified. So there's basically 2 operations. Edit the code, give me completions. You see that like this kind of like world of source files evolves over time. And there are 2 ways you could model this sort of world. One is kind of like a blob of mutable state. So we say we have like a giant hash map which maps paths to file contents, and we have a mutex around each file, and whenever we modify something, we just go look a mutex, modify stuff concurrently to everything else which is running in your compiler. And that was the architecture used by the Rust language server, the original implementation of LSP for Rust. And that is horrible because, okay, let me take a step back. It is not horrible. It depends on your goals. If your goal is to get something out of the door quickly, then that's actually, that's an okay solution. But if your goal is to build some kind of infrastructure which is going to last, then that is horrible because it greatly expands the state space of your system. Because now, like you're completing completion, and the source text of the files you're working with changes from under it. You don't have isolation in terms of like database transaction ACID properties. And that makes, and this is like bad because most of the time, you aren't going to have arrays which erases your completion. So most of the time, the code will be working correctly. But once in a while, in a particular horrible interleaving of concurrent events, you are going to have a crash. And it's going to be a nightmare to debug that, and you won't be debugging that, and those crashes will be residual in your system, and they will accumulate over time. Essentially, what you have is that you will have 10,000 latent bugs, such that the probability of each bug is like 1 in a billion, so it is impossible to debug, but at the same, because there are like 10,000 of those bugs, people will be constantly hitting all those edge cases. You realize that, hey, this is not good. And a good solution there, I think, and what Rust Analyzer is doing, is to guarantee that a system always evolves as a sequence of consistent snapshots. So whenever you write, or whenever you compute code completion or go through definition or whatever, Rust Analyzer actually takes a snapshot of the system. And while all the logic is running, you can rely on the snapshots being consistent. So this removes this time dimension from the system. You don't write a compiler which needs to deal with mutable code. No, you write a simple standard compiler which has a very static view of the world. It's just that, once in a while you change that snapshot, you advance that snapshot. And again, this is kind of like big architectural decisions which has implications for everything. You cannot really go back and change it later. It's easier and cheaper to write a separate system because that's exactly what happened. I tried to contribute to RLS and I figured out, hey, actually, I want to add this small feature, but it seems to me that the fastest way to add that feature isn't to hack with RLS, but actually, to complete my half-written Rust parser, to glue LSP to it, and then write a feature on top of that, because the architecture is going to be more conductive for support and features. And this is also, so coming back to what I was saying previously, TigerStyle applies if you're building a distributed database, if you're building something else. Learn from TigerStyle, but not necessarily apply to it. And I think some people might take it as like, okay, like just TigerStyle is like, it's like really only building databases, but otherwise we don't need it. So this is not true, because the thing here is if you optimize for the quality, you at the same time optimize for the speed of development. Because over time, all those shortcuts you took before, they will slow you down. And kind of like, if you have flaky tests or something like that, one flaky test is not a problem. But 10,000 flaky tests means that you cannot advance your CI at all. And at a point where you have 10,000 flaky tests, it is actually too late to fix it. Because probably the tests are flaky due to some architectural flaw somewhere in the middle of the system. The problem isn't that the individual test is flaky. The problem is that your architecture allows you to express flaky tests. And at that point, kind of like development slows down. It doesn't grind to a halt. You could always ship more features by hiring more programmers, by throwing more brains at a problem, but it really is going to be like, fighting with your past self. In contrast, if you do more of like workflow approach, if you actually think through how you are going to test your system in 10 years, then in 10 years time, you realize, actually, I can add features and everything works, and I only need to worry about the new feature I'm adding and not about all the bugs in the million lines of code I have written. Because this is actually, I think, one of the reasons why it is much easier to work on the greenfield system than it is to work on a mature system. In that, in a greenfield system, you implement a feature, and the size of your feature is comparable to the size of the rest of the system. So you only kind of like solve so many pre-existing bugs. In a large, huge system, well, the feature itself might be of the same size, but the size of everything else is drastically larger. And if that everything else is not rock solid, then the effort you will spend to wrestle with that everything else is going to completely dominate the effort to actually ship your feature.
That does make a lot of sense, and thanks for adding the practical example, because that adds a lot more value to what you were trying to describe, right? And if I understood correctly, there are a lot of ideas about, of course, there is some alignment with test-driven design. There's something coming from functional programming where you think about pure function, how you can test it, keep the interfaces clean and keep the side effect things at one place so you can also test them in a cleaner manner. There's also some parts of, how do you say, like formal verification, like thinking about a very small model of your code and then verifying the design by running like a simple simulation and all of that. And that's really powerful, and that feels really practical, as in, how can I apply these mental models to my own problem? And of course, as you said, working on a legacy system where a lot of other decisions have been already made and you have to just add like on top of that. So in that sense, I think you don't have that kind of flexibility. But if you're working on something greenfield, you can make those decisions, and optimizing for quality, it makes a lot of sense. The other point you mentioned about, if you optimize for quality, adding more and more features is easier, even faster, because that adds to, improvement of developer velocity. I think the main problem is people don't measure, how much all these bugs and, the backlog items or the technical debt impacts the developer velocity at all, right? They think of incremental features, they try to cut corners and, make some design decisions that do not make sense. And then when problem comes, there are more corners to cut. And, it becomes like a pile of bad decisions, and then you have to somehow support it. And I think that's the also main problem why people keep complaining about all the monolith applications, because it's not that the monolith itself is bad, but it's probably a result of all the bad decisions made by hundreds of people over tens of years, right? So I think that's really practical. Would you agree, or there are some things to add?
very much sticks to that. But actually, kind of like this is a tangent, and I realized that we kind of like agree that here we are going to go like really deep on like assertions and static allocation. We went up all the other way around, super high level meta stuff. But sorry. Okay, so you said something about measuring, and I kind of like used to think that hey, yeah, like measuring is good, but today I like somewhat skeptical about these like empirical and data-driven decisions. And that's actually goes back to blog post by Greta Huar, like the original creator of Rust, for like language design. And okay, I'm going to like horribly misrepresent this blog post, and probably Greta said something much better than I'm going to say. But the bottom line there was like, yeah, there is like this question of empiricism in language design. You design a language and you want to like run a user study and to kind of like arrive at numbers saying like, okay, like statistical programming improves programming velocity by 27% relative to object-oriented programming. But if you extend your object-oriented programming with closure capabilities, then the gap closes to 5%, and like allows you something like that. And the first of the post was like, kind of like this doesn't really works in programming language design. It all boils down to taste and to historical inertia, because programming languages are kind of like complicated beasts which are very hard to steer. It's kind of like, it's kind of like Titanic ship versus an iceberg. Like you see the iceberg, but you can't really immediately shove the ship to the side because, well, you should have done this 10 years ago. I don't really believe in the measuring on that point, and also in my personal programmer's journey. I don't think it ever happened with my design practices or whatever, where I read a paper and there was 2 graphs or 2 numbers, and I was like, okay, so number on the left is smaller than the number on the right, and bigger is better, so I'm going to apply the practice which is on the right. It's not how I operate. And okay, maybe this is wrong, but what I realized is that what really works for me is just thinking from the first principles. To give back some concrete example, going to that idea of doing a release every week. This was very much inspired by Rust, because I made the tool for my first project, IntelliJ Rust plugin. So okay, so I'm writing this plugin. I kind of want to do some beta alpha release for people to play around with, so I'm going to do releases. I know that Rust does weekly releases, and there was a blog post at some point that said, hey, we kind of stole this idea from the Chromium team or a Mozilla team. I don't remember who first did this evergreen browser, but basically, okay, so we did that, and we do 6-week release cycle, because having predictable release dates is a great multiplier, because you don't have to think about shipping a feature in a particular release, because okay, I don't have to pull an all-nighter to complete this feature by tomorrow, because, well, if I don't do this, then 6 weeks from later is going to be a new release. It's not a big loss. So that made intuitive sense for me, despite the fact that at that point I've never actually built any production software with releases. And I was thinking, okay, so yeah, that kind of makes sense, but why 6 weeks? Why not every Monday? And I think that, okay, so let's actually do this every Monday. Well, why not? It kind of seems like the logic continues. And yeah, I tried it and it worked. And again, 10 years later, I'm telling on a podcast that, hey, this is my biggest discovery in the entire programming career. This really is a secret sauce which I apply to every project I build, because that was true for IntelliJ Rust. I also did the same for Rust Analyzers of massive force multiplier. The first thing I did when I joined TigerStyle was say, hey guys, you don't have a release yet, so you really should do a release. And what's more, you should do a release every Monday. And that's been huge multiplier at Tiger. So again, that's kind of from a first principles thinking, hey, what are the actual forces here? What was going to happen here if I do this or that? There is no measurement of velocity. So yeah, that's kind of my big, I don't know there. Other than that, yeah, like a lot really depends on the historical context and on the forces and actions which happened before. And this is, I think, actually like the core idea about this, like monoliths versus microservices, because like Conway law is a thing. Your architecture of your source code is going to be reminiscent of the org chart of the organization which develops the software. And I mean, if you have like multiple teams and they don't communicate with each other, but they all together park on the same shared code base, that's going to create a pain. And adding a network boundary, adding an API boundary, which corresponds to a boundary in your org chart, actually can be like a pretty smart choice. And so, like, if you don't do that, like, yeah, you might end up with a monolith which doesn't have, like, a clear structure. Because this is, I guess, so if TigerStyle is a meter about how you like write software, then I'm going to talk about like meta layer. Because what I often see as a failure in systems is the loss of the culture, the loss of distinctive way of doing the system. Like usually, a system has a founder, and the founder has like very clear idea how the system should work. These ideas do not necessarily match TigerStyle. It might be a build fast and break things kind of founder. But still, like, there is like this idea, hey, we do this. And while the team is small, that ideology continues. And when the team grows, there is very often loss of that culture, of that idea how we write code there. And if you take a move fast, break things kind of show, and you add a TigerStyle person there, and this shop doesn't have a good manager, the TigerStyle person will destroy productivity. It will actually make the software worse. Because like even if I believe that TigerStyle is better than a move fast break things, what really matters is that there is a coherent vision for the system. And this vision is actually enforced by everyone on the team. So that's kind of goes back to the question of like my edit here. What attracted me more to Tiger Beetle is not even the TigerStyle itself, but this very explicit process of engineering the engineering process. Because I'm pretty sure that Tiger Beetle isn't going to suffer from that problem.
Interesting. And let's go a bit deeper now because we are in the realm of philosophy and high-level discussions. So let's take an example, right? Let's say we have to design a simple chat application, but really like low latency and high scalable because there are going to be a lot of users. And let's take this application and try to implement or apply some of these principles. Like first one is like simplicity. So first is how do we define simplicity? What are some smells where we say that, okay, now simplicity is not there. There are some complications or complexity involved. The second one is how do we think about static allocation? And the third one, which is probably the most interesting one at this point after the Cloudflare outage, is assertions. So how do you sort of start thinking from this high-level problem that designing a chat application and break them down and think about these three things and implement this application?
Yeah, so, yeah. The main thing is that like you really need to like understand deeply the problem which you're going to solve and the problems which you aren't going to solve. And in this sense, kind of like chat application feels like it's maybe not a crisp enough formulation of a problem. And this is kind of like the thing that I'm not familiar with this domain. So I don't really like understand what is the core challenge of building a chat application. So probably like, if I actually were deep in the domain, that my idea wouldn't be like, I want to build a chat application. My idea probably would be, hey, I want to build an application which guarantees security, where like, everything is end-to-end encrypted. And then there's like, one way of doing this. Or maybe I'm like, okay, so I want to build a chat application such that I could have a chat room where every single person on the earth is present, chat rooms which scale to like billions. And that's like, going to be another kind of application. So I think that's kind of like the first point to achieving simplicity is like, know yourself, know your enemy, know your problem. And it's gotta be like, some like the crisp notion of what I'm going to solve. Again, examples from real life. When I was like designing like Rust Analyzer, I didn't want to like, build, like IDE for Rust. Because if you want to build like an IDE for Rust, you start with some GUI things like Glue, like Cargo, or C, whatever. No, I had like this very specific requirement that I want to type a little bit of text into my program, and I want to see up-to-date information about the state of my program reflected, and I want the computation to get there be proportional to the size of my edit and not to the size of the whole text. So that's Rust Analyzer. TigerStyle, it's the same. It's not let's build a database. It is let's build a database for financial accounting which solves the problem of contention. And that's kind of like how would I approach this, building chat application problem. I would probably think, hey, actually, I don't yet understand the domain. I cannot explain the secret sauce of my application, so I need to like study better. And once you get that, you will actually understand which parts are essential and which parts can be removed. Again, one of the biggest simplification of Rust Analyzer is that it never writes anything to disk. It is fully in memory, and that's kind of like massive productivity boost because you don't have to deal with like serialization, deserialization. You have like classical currency in your application, etc., etc. Massive simplification in TigerStyle. It doesn't have SQL. It comes with this language for financial accounting and only for financial accounting. And some people might say, hey, but I kind of want to solve a general problem. But no, that's kind of like where simplicity lives. You don't want to solve the general problem. You want to solve a very specific, very narrow problem, but you want to make sure of two things. A, your problem is actually relevant, and there is perhaps an inverse relationship between how important problem is and how big it is technically. It seems like the most challenging problems in terms of performance are actually like, most simple. I mean, like financial account, there's like nothing. It's like transfer accounts, like 5 fields, but the entire database is built to support it. Again, so assume we have something like that for a chart. How we go deeper, how we go to, let's say, static allocation. And here, again, what I want to emphasize that static allocation isn't a goal of TigerStyle. Like they think it isn't, hey, we want to do static allocation, therefore we use it. No, static allocation is a consequence of another thing. And okay, so this is complicated, so I will spend some time explaining this. And for listeners, if you are aware of my hard mode Rust blog post, it will be useful to keep it in mind because both hard mode Rust and TigerStyle do static allocation. But hard mode Rust does static allocation in a wrong way. I didn't understand it. And now TigerStyle, I actually realized that, hey, you want to do things differently. So what is the actual thing which we are tackling here? That thing is physical limits. Our computers are finite. There is only so many CPUs, so many RAM, so many networks, so many disk space. That means that whatever program you write, it is going to have some limit. Past certain amount of input data, your program will crash and burn. Another question is, okay, do you know the limit? And for most of the programs, the answer is no, I don't know the limit. And that's kind of like funny, like, programs crash sometimes. And this is also true that program crash is not a problem. Like, a lot of people like to say that, hey, we want to write bug-free software. Like, software should be bug-free. I think it's completely false. Because if it were true, then we wouldn't have any software at all today, because all software has bugs. Like even TigerStyle has bugs, although very small amount and relatively benign ones. I guess that one was wrong, because the thing with TigerStyle is that it probably has some bugs, but we don't know about those bugs because if we knew, we fixed them. But highly likely that those bugs will be benign in the sense that all they're affecting availability, not safety. Like, software has bugs, and this is fine for most cases, and you want to balance the effort to develop software with features, bugs, et cetera, and in some domains, those things are more important. So in the domain for which we invented TigerStyle, financial accounting, it is pretty important to have as little bugs as possible. It really is important to prevent system from crashing, including due to running out of resources. So for our domain, we actually do want to know explicit limits of everything. If there is like certain like thing in our code base, we want to be able to say, hey, there might be at most 1 million of those things at any given point in time in our database. And if 1 million plus one thing attempts to get created, what we will do is that we will politely fail that single request instead of like arbitrary crashing, arbitrary slowing down, etc., etc. So yeah, that's kind of like a thing. You need to account for every variable parameter in your system. And then if you know that, hey, there might be at most 1 million of those things at any given point in time, it becomes just simpler to go and have an array of those 1 million things and juggle them in an array, explicitly accounting for how many of them are in use and how many of them are free, as opposed to, allocating a new thing on the fly on the heap once you need it. That is the idea of static allocation as we practice it in TigerStyle. We want our system to be operationally enjoyable. We want it to be operationally reliable. For that reason, we want to be explicitly aware about the limits of our system. And because we are aware about the limits of our system, it is actually easier to remove dynamic allocation and explicitly allocate all the resources given our limits. And this is actually funny because, so the way I like to say it, it is true that TigerStyle has, a static allocation, but it's also true that we don't actually know how much memory we use. There is no, a single global constant which says, okay, TigerStyle uses like 16 gigabytes of memory and like everything fits in those 16 gigabytes. No, it's rather, you say, okay, so we have like the amount of messages equal to the amount of clients we support plus the amount of replicas we support times 2 for send message buffers plus 5 messages for journal. And then in addition to messages, we have account cache, and account cache has to hold at least this many accounts, blah, 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 blah. So you for every object, you kind of compute incrementally the limit, and the limit is also a tree thing, like how many grid writes do we need to have? Well, the number of grid writes we need is the number of grid writes for journal plus the number of grid writes for Scrubber plus the number of grid writes for compaction, etc., etc. And once you sum all those numbers and multiply by the sizes of the things, you get the amount of memory you allocate. But that number is kind of implicit in Zeek's compile time logic. It isn't hard-coded upfront. And that is the difference with hard-mode Rust. Because in hard-mode Rust, I went in the opposite direction. I said, okay, I want to do static allocation, so I'm going to allocate 1 megabyte of memory and then write my ray tracer using an arena allocator using that 1 megabyte. It gives you this guarantee that yes, your system is not going to use more than 1 megabyte. But it doesn't give you that guarantee that your system wouldn't run heads into some hard limit. So my hard-mode Rusty can fail with logical out-of-memory error. TigerStyle cannot fail with a logical out-of-memory error because we explicitly account for everything. And yeah, that's basically it. So going back to the chat example, yeah, so this is kind of the question, do you need that level of reliability? And if your chart is to power some kind of mission critical applications or something like that, probably yes. Probably you do want your application to have static limits. And that means that you need to say, okay, so there's going to be like at most this many people chatting at any given point in time. And kind of like if more people join, I will actually reject those requests. And once you have all those limits for the inputs, you actually will be able to derive all the internal limits and then follow the static allocation, which again, it doesn't mean, so this was actually like one of the biggest updates for me when I joined Tiger, because I was thinking that like static allocation is going to be horrible because I mean, it sounds hard, like you really need to like, know a count of every item in a system. And if you make an error there, then your system will fail. And like, you also constantly refactor the code and it also changes. And it feels like, it's impossible to get right. But the trick is static allocation is actually very easy because it is compositional. It is kind of like, how do you make sure that the amount of water in a bathtub is constant? One way to do this is that you could like frantically count any like hydrogen and oxygen atom in your bathtub, and that's kind of like a lot of work. But another way is that you could like, look at the tap and make sure that the tap is closed, and then look at the sink and make sure that the sink isn't leaking. And then kind of like the amount of water stays constant by the virtue of like, matter not getting created or destroyed out of thin air. So when you code this system with static allocation, what you actually are doing is like this compositional, okay, so I have like this thing and I transform it and then I move it elsewhere, and you don't create or destroy values. And that kind of like gives you this guarantee that, hey, it all works out in the end. So this is kind of like a big thing is that like you should try static allocation just to see that it actually is much easier than it seems. And honestly, this is surprising. Whenever I code some new thing for TigerStyle, I'm just writing code. I'm not really thinking about allocation. It kind of just comes naturally because actually you only need to think about like boundary conditions, and then everything else just falls into place. Although I do have some doubts whether this advice is fully generalizable. Because the thing with TigerStyle is that it is a distributed database, so it gets to cheat. The actual data is stored on disk. And what is stored in memory, what we are allocating statically, is just some indexing data structures which point to the actual data. And what we say is that the size of the working set is constant, but the total amount of data might actually be pretty much unbounded. So we say that, okay, a single message to TigerStyle is 1 megabyte, so it adds up to about 8,000 transfers, and that is a chunk of work which is the actual physical link. You need to be able to process 8,000 financial transfers with the memory you have, and then write to disk. But then this train of transfers arrives one after another, one after another, one after another, and you end up accumulating on the persistent storage a significant amount of data. When you are writing something like a compiler, I'm not sure you necessarily will get this property of working set being limited. It might be the case that, hey, actually, like, your programs might be arbitrarily large, and you need to keep the entire program in memory. And there is no way to say, like, okay, so we only allow like 5,000 functions, and like a single function can have like, it goes like 5,000 instructions. But okay, maybe you can do this. So coming back to our chat application, I think it might work if you say, hey, I do have like a very strict bound on like how many messages I'm seeing on the screen right now. So, okay, like we could say, okay, user can see up to 1 million messages, but not more. And you can say, okay, like we have like, this many users, and if we have more users than that, and like each user is just a counter and not their ID or something like that. But yeah, the overall rule here for like how to apply static allocation principles for designing software is thinking in terms of like bathtub equation, thinking about how data flows into the system, how data flows out of the system, and how much data needs to be retained. If it is true both that A, data flows into the system in bounded chunks, or you can make it flow into the system into bounded chunks, and B, the total amount of data accumulated in the system is bounded, but yeah, go for static allocation. It's going to be much, much simpler.
Okay. I think that makes a lot of sense. And I think I understand, how what you wrote or what you experimented with Rust hard mode and, what you have in Tiger Beetle is kind of opposite. And so you need to think about your domain and kind of have some bounds within your domain and then move further by composing them. And I think that makes a lot of sense. But I've been thinking like, for example, how does it relate when, so let's say you say that, okay, this is the amount of memory and resources I need. But let's say some systems are really spiky or some systems, depend on the behavior of the upstream. In that sense, something like how a list works, right? Like I give like a size and then whenever it's about, let's say 75%, it doubles its size, creates a new list and things like that. Having like strictly defined static allocation versus kind of a hybrid mode where you statically allocate and whenever something reaches above a threshold and you just double the resource. So it's again like statically allocated, but it's still incremental in a way. And with that, I also wanted to ask, how does like vertically scaling work in this sense when you really need more resources as compared to, failing the application?
Yeah, one trick here is that like you often can make systems like, auto-scaling in this sense. Tiger Beetle is a good case here because we are a batch system. So one request to Tiger Beetle is 8,000, it's 1 megabyte message which contains 8,000 transfers. And this is the trick. If the load is low, then the requests which go into the system, they are actually mostly empty. There's like, just 1, 2 transfers. And we process those requests very fast and give user the answer. Now, if the system goes under the load and the user starts to submit more transfers, then while we are processing the current batch of transfers, all the following transfers, they are accumulating in memory on the user's machine. And when they are ready to submit a new transfer, that is a new transaction, a new title request, I'm confusing words, that is when the old request is finished. The next batch they are going to send is going to actually be bigger. And in Tiger Beetle, there is variable cost to process the batch, which is like depending on how full it is, but most of the cost is actually pure batch. So we get this like automatic batching behavior where as the load increases, our batches become fuller and fuller, and we'll be able to provide, to produce more results using the same underlying machine resources, a little bit more resources. So this kind of like, automatic batching of things is a better strategy than like, growing your list 2 times. Because if you grew your list 2 times, well, now you need to spend twice as many resources. With batching though, if you make sure that most of your costs are amortized per batch, that a linear increase in the amount of events you process doesn't correspond to a linear increase in the resources you need. Okay, then the second thing, like how do you scale vertically when the load increases? Well, this is really simple. You write fast code because computers are incredibly powerful. If you are able to use 30% of the silicon inside your CPU, you're probably going to have way more performance than you need because most of software is horribly inefficient. By actively thinking about performance, by actively trying to work together with your CPU rather than against it, you could actually push this vertical scalability pretty far. Again, it is kind of a question of do you need to push vertical scalability far, maybe it is going to be easier at some point to scale out horizontally. And this is true because, again, like going to the peak performance takes a lot of time. For TigerStyle, we don't really have the choice because the problem we are solving, like the engineering problem, is contention, is multiple transactions which hit the same few accounts again and again, because that's how your actual transactional workload looks like. 80% of transfers are going to affect like 20% of accounts in the best case. In the worst case, you will have a table with like only 5 rows in it. If you think about like the switch between like big banks or something like that. So you'll be like hammering that very small working set with a lot of load. And if you try to horizontally scale that, well, then your system is going to be much slower because ultimately data needs to live somewhere. And if you need 2 pieces of data for your request, and the thing about transactions is that they always from account A to account B, so there's like 2 counterparties. And if those counterparties are on 2 different shards of your horizontally scalable system, then it's going to be a lot of time to like physically move the data around. Kind of like that here is like really thinking about contention. If you can design the contention away, that is good, and you probably should do that. And that means that you could optimize your system to a satisfactory degree and then scale out. But if you have contention, well, then use TigerStyle, because that's why we build the system. Because we don't want every person in every team go and look at the statistics by the perf tool and like count cache misses and all that stuff. No, we will do it for you, and then we'll give you database for account. Because accounting is kind of like the central problem for the case of high contention. Like almost anything which fundamentally requires solvent contention is one way or another just counting things.
Very powerful. I think I get the idea, and the way Tiger Beetle is solving it is also very interesting. In the interest of time, I would love to touch base on the third point, which is assertions, right?
Assertions.
And
yes.
And I would love to take this example of a very specific chat application. Let's say we are in a gaming environment where, there is a chat room and, everyone is trying to send messages and also play the game, some sort of, Counter-Strike or something like that. And assertions can make sure that the game stays in the correct state. But sometimes they may also break the entire chat application, right? So I wanted to understand, and with this recent Cloudflare outage, a lot of people had different opinions, as in people should be able to, or systems should be able to, gracefully, handle failures instead of just crashing and taking the entire internet down, versus some people were more towards, okay, having assertion makes sense because you don't know what state your application will be in. Talking about specifically this chat application, there can be multiple states where the application may reach. For example, a banned user joins the room and tries to send a message. Is it the right case for, an assertion where we say that this user state must be not banned or something like that? Or in some cases, it could be that user is just sending a bad message, which is not supported. So having assertions means that we are impacting the chat application for all the other users, versus taking the chat application in a state where a banned user is able to send a message, which can be malicious or a bad message. So what is your take on that, and how should we approach assertion in this specific use case?
Kiwi, I probably should ask you whether we are going to do volume 3 of TigerStyle, because honestly, I totally can talk for hours about this specific thing. So there's like a lot of ground to cover. I think, okay, so what is the most valuable thing to say? Okay, so the most valuable thing to say is that there was a choice between availability but being incorrect and safety. So you kind of like you can choose to be safe, or you could choose to be available. And that depends on your domain. And in some domains, safety is more important. In some domains, availability is more important. Again, Rust Analyzer, TigerStyle. I always talk about Rust Analyzer and TigerStyle just because they both have this meta thing of having very strong idea about how to build a system, but the actual meta idea of how to build a system is completely opposite, because Rust Analyzer is about availability and TigerStyle is about safety. So, like, if you're building an IDE, then your IDE crashing is much worse result than your IDE giving you like incorrect completion. There, you want to do like this, okay, let's ignore errors. If you are building some kind of like, command line utility, which is like a filter, like, it treats data and it spits out the answer, and it's very cheap to rerun this utility, then actually, like, you could say, okay, I will like do assertions because the cost of mistake is really small. I'm not going to bring down the entire IDE, or I'm not going to bring down the entire internet. I'm crashing this like isolated thing, which is like can be easily rerun. If you're doing like financial accounting, you need both, and that makes it hard. And then you do the simulation testing. So that's kind of like the basic thing. The second thing, it really helps to think about error philosophy, let it crash, on kind of like medium level. So kind of like, there is like this probably like bell curve meme here is that, some people don't know about let it crash. Some people are like, okay, let it crash. And then some people are okay, let's maybe not crash. The thing is, with let it crash philosophy, with assertions, there are two things you need to keep in mind. One is where you check the invariant, where you crash, but also what is the boundary where you recover. The secret sauce behind error is not that it crashes on error. I mean, like every program crashes on error. Like my browser crashes on error. Like it happens. The magic sauce behind Erlang is that it has a process abstraction, and Erlang process is not a Unix or POSIX process. It is like this Erlang runtime thing with a completely isolated heap, which can crash, which can be slow, which can do like whatever, and this doesn't affect your overall system. That is kind of like the first thing you really need to think about isolation boundaries. You need to say, okay, so I'm allowing to glue this part completely away, but I know that the blast radius is contained within this room. And again, going back to my favorite example of Rust Analyzer. So I said here that, hey, like the compiler works with a snapshot. And that snapshot, by its nature, is immutable. That means that the bulk of Rust Analyzer's code cannot change the data. It cannot poison the data. So the way Rust Analyzer works is that 99% of the code is within a catch unwind function call, which catches not only like errors, which you like return, but actually panics. And that means that Rust Analyzer has like a ton of bugs. Write some code that like parser choke on it, and then like type checker does index of bounds exception. Like it happens like all the time. And then that catch and bind like catches the bug, like logs an issue if it is like a development build. So like it's me like using Rust Analyzer. It also like shows like a really ugly error message, which is really ugly. So I just have to fix the bug on the aesthetics round. But that's it. Like if you're a normal user, you're not seeing that. You just see that, hey, you have like 5 items in your completion list instead of 6, and you don't even know that there should have been another one there. But again, the idea here isn't like, let's wrap catch and bind and that's it. No, the idea is that you introduce a strong isolation boundary. And in case of Rust Analyzer, the isolation boundary is the fact that the snapshot is read-only. So there is this 1% of the code which is responsible for like evolving snapshots, for like actually saying, okay, we were at point A, now we are at point B. If that code crashes, it like brings down the whole system with it. And there we do like assertions which actually like immediately kill the thing. Going back to assertions, Rust Analyzer, but not TigerStyle, uses the assertion style from SQLite. Like normally, if assertion function is invoked, you're false, like you crash the process. the assertion with a rationalizer which is called, okay, oh, it is called always. So you could write assert, but you could also write always. This always returns you the value you passed in. So it is essentially a identity function. And you could actually branch on the result of that always call. So in development builds, that always is compiled as an assertion, and you go and crash the process, and then you go and fix it. Because it's kind of like, very annoying to like code Rust if your IDE crashed. So it's kind of very powerful motivation to fix it. But in production for users, we say, okay, if this doesn't hold, there's clearly a bug, we do a log. We don't do telemetry, so okay, we'll have to rely on someone actually tweeting about that log. But anyway, we kind of like do a recovery action here. We like return some result. That's kind of like the first thing is that you need to think about isolation boundaries, because the tricky thing about that crash is not crashing. Crashing is easy. It is coming up with isolation boundaries. And the second thing I want to cover here are types, because there is like, in the minds of some people at least, a certain dichotomy between types and assertions. And I think I managed to capture very crisply what types are good at. Because when people who love dynamically typed languages, like, I should give an example of dynamically typed language, like maybe like JavaScript or like Python or Ruby, but I realized I cannot do this anymore because all those languages now have types. So like, sorry, like dynamic typing has lost. But anyway, so like people, from dynamically typed languages saying that, hey, types are useless because types only catch errors, or like mostly catch errors which are, blindly obvious. Like, you call a method and there is no such method, like type error. And like, if you just run that code once, it's like obviously blow up. So types cannot really improve correctness of what you're doing. And I actually agree with this, because I think types are good at catching errors in a code which was never run. Because if there is a type error and you run this code, it blows up immediately. You go and fix it. Types only help you for the code which is like in a completely cold path, which is never executed. And you might think that, hey, like, like all the code is executed all the time, but that's not true. There are genuine code paths which are extremely rare. For example, error handling. You like do something and then like there's an error and you handle it, but in reality, you aren't going to see the error. Your read call isn't going to return you like, some error. I don't even know what are the errors possible from the read call, because I've never like seen that happening. Except that one day it will return an error, and that will engage your error-handled code. And if that error-handled code is written in a dynamically typed language, you realize that you're calling a method on an object which was refactored 3 months ago, and you will blow up. That is where like types are crucial, because they give you like usually very weak correctness guarantee that, hey, like the method you're trying to call actually exists, and it has like, this number, this many arguments, etc., and it is like both useless for the code you actually run, but for the code, it still probably is going to crash in some way or another, but there's like minimal guarantee that it is not completely incorrect. Like the idea here is that because cold code is exactly like, cold, dark code. This is where the bugs live. Bugs like cold, moist, poorly lit places. You want to avoid that code. So this is like the idea of like crash-only software. You don't have shutdown routine in your application, because shutdown routine involves a tour of cold code. Because, okay, you shut down fairly frequently, but every time you shut down, your system is in a different state. And like this state of doing shutdown is what generates rare events. So instead you say, okay, like my application just like crashes. The only way to stop the application is just to like, kill the typers. And this is how That's the lens works. We don't have graceful way to terminate the thing. Like, you can't type agent or something like that. You just have to secure the process. And that kind of removes all those kinds of things. This is what you do if you don't have the isolation boundary, but you have assertions. You need to make sure that you run every possible code path of your application. And how do you run it? Well, two ways. Either you design your application to not have code paths, but that's probably not possible, or you do deterministic simulation testing. Because that is the magic about deterministic simulation testing. This is the synthesis of the idea of static typing and dynamic typing. Yes, dynamic static types catch all the stupid errors, and if you run code at least once, you will see it anyway, so you don't need static typing. But no, actually running code at least once is one hell of an task. There's going to be tons of code which is never executed, but that's why you need to implement a testing system which can systematically explore all the code paths for your application to make sure that all the assertions are actually correct. So that is the thing. We don't really have big isolation boundary in type. Well, we do have a big isolation boundary. It is always safe to crash and restart a process. And if error is transient, then this is completely not a problem. But we don't have more fine great isolation boundaries failing an individual request rather than failing the entire system. But we compensate for that by writing a ton of different fuzzers, where each fuzzer systematically explores the problem state, and we have a pretty good confidence that all our assertions are actually true. But we don't disable assertions. We keep assertions enabled at runtime because, for us, safety is really important, and we'd rather crash than give an incorrect answer to the user's query.
That makes a lot of sense, and I have many questions to ask there. But as you said, in the interest of time, I think it makes more sense to do a volume 3, and it's going to be interesting. But yeah, thanks a lot for joining me today. I just have one last question. What is the secret sauce behind your energy? Is it just caffeine? Is it a lot of passion for this domain to talk about? Because I know that you have 2 more sessions to go on, and you have this incredible energy, which is infectious, amazing. I'm seriously impressed.
I just love programming. I cannot help it. Isn't it fun? You
it is.
Type something, and then pixels light up, and then it's even useful. This is the most incredible thing. When I was studying, I came from a mathematical background, and I was I can write a program which multiplies to polynomials. Isn't this wonderful? It's super excited. But now what I'm doing is actually useful for people. This is really incredible, and I can't really understand how you could not be excited about that. I've been doing programming for a long time, and still it does happen pretty regularly that I stay up all night, programming something, or writing a blog post, or just thinking about some technical problem because it is that exciting. I don't know. I just love this stuff.
Awesome. Yeah, that's awesome. But yeah, thanks a lot for joining me and sharing the amazing insights. And we should stay in touch for the volume 3 and, see what our viewers think. And for our viewers, if you like this episode, please don't forget to hit the like button, subscribe to the channel, and, until the next episode, thanks a lot.
Yeah, thanks again for having me.